Hello and welcome to lecture number 9 of ITEC4017. This is a course in photorealistic and non-photorealistic rendering, and I am your instructor as always, Leslie Eisted. In today's lecture, we are going to take a look at something called Toon Shading, which I think you'll find very interesting. Just a couple quick notes before we dive into some material. Note that assignment 4 has been posted, and that is on Toon Shading, which we are doing today. And that we'll get that final project content posted real soon. Just to give you a heads up as to what to expect with the final project, there's going to be a choice of different scenes that we ask you to render using various techniques that you've learned throughout the term, and then you'll be submitting those final scenes along with any of the materials you use to create them. So it should be fairly fun. All right. So we want to talk today about Toon Shading, and this is when we're thinking about non-photorealistic rendering, probably one of the most commonly thought of. And if we were to think about what do we even mean by Toon Shading, well, really we're thinking about cartoons. And cartoons, it's an interesting word because it actually has several meanings going back over art history, but when we think about cartoons, we're thinking about modern cartoons, things that have a very simplistic stylized illustration. They're typically comedic in nature, though that's not necessarily required. And so you've got the simple representation, you've got strong visible outlines, usually in black, but not necessarily so. Sometimes it's just in a darker tone. You also have a simplified or reduced set of colors. And sometimes you have so few colors that in order to represent the shading on something, they might use dithering or some kind of patterned texture, like a hatching or a stippling, to kind of give you a sense of the 3D shape. But actually what's interesting is if you look over the history of cartoons, some cartoons are even simpler than that, and they have no shading at all. So this is a black and white sketch from Felix the Cat back in 1923. And so you can obviously see here this has no color at all. We see very simplified forms and very bold use of tones. So there's only black, white, and a couple shades of gray here. There's no sense of 3D. Now they've added some highlights to these spotlights, but you're not seeing that smooth shading that you would expect to see on this object in real life. So just a few examples from history again. So this is actually from Looney Tunes, which you may or may not have seen. This is one of their more famous ones, which is from an opera, actually. I'm not familiar with the name of the opera at the moment. But again, you see very simplified forms. We have strong black outlines. And what's interesting about the Bugs Bunny cartoons is that all of the actual characters or animated pieces are incredibly simply shaded. So that is, they're solid colors. There's no highlight, no shadow or anything like that. And they tend to be rendered on top of painted backgrounds, which are actually stills. And of course, since cartoons like this actually date back about 60 years, 70 years, 80 years or more, these were actually hand-drawn, and a lot of the times these were rotoed and done actually on pieces of film that were overlaid on top of the painted background. So this was a lot of work. And then you move into the Disney era, and you'll notice I don't have any older Disneys. And the reason why you don't see any older Disneys is because they kind of fall into the same category as this Looney Tunes cartoon, where you've got really simple, solid color shapes or characters on top of painted backgrounds. But some of the newer Disney film animated cartoons actually depict some shading now. And so this, of course, is The Lion King, the animated one, and you can see in the lion's mane and in their body they've actually used some shadow tones, and instead of using strong black outlines, they're actually just using a darker tone of the actual animal color. So the mane here is outlined in a darker shade of red, and the body here in a darker shade of this brown color. But like the previous cartoons, again, these cartoons were actually rendered on top of a painted background. Now this one is not an actual cartoon. This is actually a video game, and some of you might be familiar with it. This is Legend of Zelda Wind Waker, which, if memory serves me, was released in the very early 2000s, right around 2001, 2002. It's for GameCube if you haven't played it, but you can actually get an HD version on the Wii now, I believe. So this was a Toon shaded game, and that is, they tried to create that cartoon-like appearance with their 3D models. So if you look here, even though things are not outlined in black, and certainly there's actually nothing preventing them from doing that, it's just they chose an art style that was not outlined in black, you can see that everything is very simply shaded. So you don't have smooth shading to make the mast of this boat look like it's round. You have three distinct tones. You have this dark teal, a medium teal, and on the far edge here you have a lighter shade of teal. And it's not that this is a hexagonal object. It's supposed to be round. It's just they've simplified or quantized the number of colors to a small number to give you that Toon-like appearance. And this game actually took a lot of criticism for that particular style, but I thought it was kind of fun, actually. So when it comes to recreating this look of cartoons in computer graphics, there's actually a variety of approaches that you can take to this. And we're going to look at three different takes, actually. We're going to look at utilizing textures to help us do this, and on the way we'll be building some custom shaders, so you don't have to use a texture. You can use just a plain old shader. And then the third approach is actually doing everything in image space. So there's lots of approaches we can actually take, which means that the first two we can actually apply to 3D scenes, and the last one, image space, you can apply this to a 3D scene after it's been rendered, or you can just apply this to a photo, whatever your desired appearance would actually be. So our goal here for Toon Shading is we want to create a cartoon-like appearance, but we're going to keep our concentration on the coloration and the shading of the objects. So we're not going to be looking at outlines right now. We're not going to be looking at deformations to the shape. We're just going to be looking at, when it comes to Toon Shading, the actual way that we are coloring the objects in the scene. And typically what that means is we're going to restrict our palette to just a few small tones. So we'll have a dark tone wherever there's a shadowed area, and then a lighter tone for highlights, and then something for everything in between. So there's not going to be a smooth gradient for shading. So if you have a sphere, it's not going to be smoothly shaded. There'll be color bands representing each of these: shadow, midlight, highlight. And so one of the things you need to be thinking about when you're looking at Toon Shading is, how do you figure out what the color each pixel is actually going to be? And the color of a pixel really depends on the amount of incident light being received by that particular pixel. So we're going to be looking back at the rendering equation again and seeing how we can take that and turn that into the Toon Shader math. Now, as we saw in all of our examples looking back here, whether it was Felix the Cat, Bugs Bunny, or the Lion King, of course Zelda here's the exception, but here's another Bugs Bunny, you'll note that all of these have taken time to put these black outlines around the objects themselves. We are not going to really mention this for more than a minute or two today. This is an optional thing. Sometimes people are looking for toon shading to have those black outlines. Sometimes, like in the case of Zelda, they're not. I have even seen the case where they will use, instead of a dark outline, a bright outline to get just a different look as well. These outlines are actually optional, purely optional, so we're not going to really talk about them much today. But in our next lecture, we're actually going to dive into how to create those outlines in much greater detail, and also other kinds of shading as well. So, how might we actually create this toon shaded appearance? So, our first idea is that we're making the observation from things like this barbershop of Seville that the colors used are really bright and really bold. And that's true for the Zelda game, it's true for the Lion King, and it's definitely true for this Bugs Bunny here. We're using very simple, bright, bold, unshaded, for the large part, colors. So what we could do to recreate that kind of appearance is, why don't we just go with ray casting? It's an idea. The idea is that we can use an ambient light to set how much light should be visible in the scene, but we just won't do any shadow computation. So we're not going to perform any of the operations of the rendering equation aside from the ambient light component, which again is just an estimation of the indirect lighting. Now, what's nice about this technique is that it's really fast and it's really easy. This would be considered something like a constant light inside of something like Houdini, or you can just disable lighting altogether. So it's fast and it's really simple, and in a lot of ways, aside from the absence of black outlines, it should look very much like early cartoons. Now, the downsides of this particular technique are that you don't have any shading. Now, I know we don't want the smooth shading because that doesn't tend to be something we associate with toon shading. But now we have no shading at all. We have no reflections, and we also, as a result, we have no surface details because there's no lighting computation being performed to figure out how much incident light is affecting the color of this particular point. So if we were to actually create a scene in Houdini and then render it using this, that's what you get. And if we were to add some black outlines to this, look bad. I'm not going to say it would look good, but I don't think it would look bad. Now, we could easily get the outer black edges just by doing something like the Sobel filter we talked about in our last lecture, and then multiplying the edges by this image to get black outlines, but that wouldn't give us any interior details. And if you look back at these Looney Tunes cartoons, yes, they are simple shaded. There's no concept of lighting, but we do have black outlines, and we also have some interior details as well, and that's completely missing from this image here. All right. So that didn't work. The next idea that we have is, why don't we just use a texture? So what I mean by let's just use a texture, I mean open up your favorite web browser, and we've got our favorite web browser here, And what we're going to do is, well, let's just look for a texture map. So what we would be doing is doing something like creating a texture map for our object and baking the lighting and the shading right into the texture. Now this is actually a fairly easy approach to doing it because you have complete control over the appearance of the final object because you've hand drawn it and baked it into the texture, which then gets projected onto the object. You don't need to do any shadow testing, and you can light the scene with an ambient light source. So it's going to be really, really fast and really, really easy to do, and you get a fair amount of customization because you can actually manually edit the texture itself. The downside of this particular technique is the fact that the lighting is baked in, which means it's static and it's not changing because you actually physically painted it onto the object. And so if you put a light in the scene, it's not actually going to impact the appearance of the objects in the scene. So this can work if you're trying to render a still scene, but if you were trying to render a video, this wouldn't necessarily be the best approach to go with. So we're not going to use this one either. So let's take a bit of a deeper dive and think about how do we actually make a Toon Shader that's dynamic. That means that if I move my light, if I move the object, the shading of the object responds to the change in the scene, the world. So that means we don't want anything baked. We need to, in order to do this, take a look at our rendering equation for surfaces. So I've brought the rendering equation over here again, and this is an approximation to the rendering equation. This is not the full solution because this is only taking into consideration certain kinds of surfaces, and there's no indirect lighting component here. But we have the sum to figure out the light contribution on a particular point. You take the amount of ambient light contribution, you add it to the diffuse contribution and the shiny contribution, or the specular lighting. To get the ambient contribution, it's very, very simple. You take the color and you multiply it by the intensity of a light. Very simple. You add it. And the shiny part, this is actually the Phong shiny equation here, but this could just as easily be the bin Phong. It doesn't matter. It's going to be the same either way. The part that we're actually interested in, though, is this diffuse lighting computation, where we are trying to figure out how much of the incident light is affecting the color of this particular point on the surface of the object. Now, when we're doing Toon Shading, ambient light should play a role if you want it to. It doesn't actually have to. But the shiny component, in this case our Phong term, is not needed because when we're dealing with Toon Shading, we are not often worried about things like shiny white highlights. How big is the highlight? And how specifically big is the highlight, and how smooth is the fall off of the highlight, because we're not doing a smooth shaded scene. We are specifically doing a reduced color, a quantized scene. So it's not to say that you cannot include this component in a Toon Shading computation, but we are not going to do that. We're going to eliminate the shiny component here. We don't need it. The part that we're going to take advantage of is the diffuse lighting contribution. So looking at the diffuse contribution in a bit greater detail, we have KD, which is the color of the object itself. I'm trying to find an object here, a wallet. So, excuse me, you have this dark brown wallet. Let's pretend it's diffuse. This isn't a perfectly diffuse surface. Let's pretend it is. And so you've got this brown wallet. So that is KD, the surface color. Then we have LD, which is the light intensity. So that is dealing with how bright the light is that is shining and trying to contribute to the color of the object you're looking at. And then in brackets here, excuse me, we have L dot N. So we take the dot product of the incident light ray and the surface normal at the point of intersection. Because what we're doing by taking the dot product is we're trying to figure out what the cosine is of the angle of the incident light. Because that is going to tell us, according to Lambert's law, how much of a contribution that light source makes to the color of that surface point. And the idea is that the smaller the angle between the incident light and the normal, the more contribution the light will make. And the further away you get, the less contribution. And anything that is 90 degrees or more should make no contribution to the color of that particular pixel. So if we were to use this particular term straight up, it would give us a smooth shaded object, like just diffuse, not shiny, no highlight. And that's not quite what we're looking for. We are looking for something that isn't smooth shaded. We want quantized to just a few colors. So if we were to dive in to this particular shader and look at kind of a code-based approach, one of the ways that we could take that computation and quantize it, that is reduce it to a simple set of colors, is to compute the actual value. So I've set C to be the color of the object times the dot product of the incident light and the normal times the intensity of the light. And if C, that computed contribution, is less than some threshold, then we'll color the pixel using some dark color because it's far away. Or the angle is really large. If, however, it's less than some secondary threshold, we'll use a middle color. Otherwise, we consider it in highlight, and we'll use the highlight color. That's actually a pretty simple way of quantizing the result of the diffuse term right here. And we can do that. So this was done in Houdini very simply. There were 3 thresholds. Each of these objects has been colored using 3 different tones. So for the dragon, we have a dark red, a medium red, and a bright red, and then dark blue, medium blue, and a brighter blue for the horse, and similarly for the torus and the sphere. One of the interesting things I think about this particular image is that the dragon, even though we have this quantized color, it ended up looking kind of metallic, even though we're just using 3 colors and there's no blending between them. So I thought that was kind of a fun result, that you get this metallic looking dragon with only 3 colors. Kind of fun. So that particular shader, whether you were to write that in a piece of code, or if you were trying to do it in a node network, whether that was in Houdini using the VOPs, or if you were trying to do that for Arnold, or if you were trying to do that in Unity, that shader is very simple to write. However, it's not the world's best implementation. there's a lot of limits that we have. For one, we've hard-coded everything about that particular shader. So we've hard-coded, and what hard-coded means is that if I want to change it, I actually have to physically change the shader and recompile it and reapply it to the material in order to impact the appearance. And that's not really something we want to do because it doesn't make your code easy to use or maintainable or user-friendly and so on. And the problem is we've hard-coded the number of colors to 3. We've hard-coded the colors itself. I know it's not written in here, but mid-color, dark color, and highlight color would actually be hard-coded values, but so would these thresholds. So since we have actually hard-coded all those values, this shader isn't that useful. We can't specify at the time of application what we want the thresholds to be or what we want the colors to be. They're all fixed. So ideally, we like this general idea of using some kind of threshold to indicate, okay, you're going to use this color, otherwise you're going to use that color. So this makes sense, but the implementation of this is not very flexible. So what I want to talk about now is methods to actually create that flexibility in the shader, to parameterize the number of colors we use and what those colors actually are, and to also give a way to specify where those thresholds actually live. And one of the common ways that you'll see this done is using something called a ramp. And ramps, we typically have 2 endpoints, and a ramp is showing you all of the values between the starting point and the ending point. So it's like an interpolation from start to end. And when you see a ramp, it's usually in like Photoshop or Houdini or any kind of graphics tool. It's presented as a kind of smooth gradient. So here we have a ramp that goes from this light powder blue to a darker blue. And I know that any value in between contains some amount of the light blue and some amount of the dark blue corresponding to your position in between the 2 endpoints. Now the ramp that I have here is a linear ramp. That is, it's every point in the middle is a linear combination of the endpoints. You could think of it as this is 0 and this is 10. And so I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very, very simple. Ramps do not have to use that kind of linear interpolation between the endpoints. You can actually have an exponential ramp, a polynomial ramp, a wild and crazy ramp with like weirdness, as we will see. They don't have to be linear is the point I'm trying to make. In fact, what we've noticed about our ramps is that you can actually have multiple intermediate points, and those intermediate points can be different values. Now, those intermediate points in most tools will be called stops. So here I have light blue on one side and dark blue on the other, and then I have a stop roughly in the middle that is pink, a light pink. And so between the left endpoint and this pink stop, the colors go from light blue to pink. And then from this stop here, pink, to the other endpoint, it goes from pink to dark blue. And I've done something different here. I've got light blue on either end and dark blue in the middle. And then I can start adding more and more stops to get more and more unique appearances to the ramps. You can create all different kinds of gradient effects using these ramps. Now what's interesting is that some tools will even permit you to have a ramp where there's no interpolation between the endpoints or the stops. So that is, it's quantized. So I could literally have this part of the ramp be, if you lie in this range, you're going to be light blue. If your value lies in this range, you're going to be medium blue, and this range, dark blue. It can be any way you want. And I can actually show you how to create these. So let's just open up a Google slide. Let's open up a blank Google slide because that's really all I want. Let's create an empty one. So I can show you how to create a ramp like that. So we'll make our shape. And then we go to gradient and we do custom. Now, to get the quantization in the ramp, I'm going to do, let's have this endpoint be, I don't know. Let's do orange and the other end be purple. Let's make them very different. Okay. Now, I want this to have a red in the middle. So I'm going to add a stop, and I'm going to place it right here. And I'm going to make this stop orange. And then I'm going to add another stop, and I'm going to place it pretty much directly over top of the previous stop. And I'm going to make it the color I want in the middle. So maybe it's this pinkish color. I add another stop. Let's add it here. And I'm going to set it to that pinkish color as well. I add another stop. When I add the stops over top of each other and then force the color, I prevent the interpolation between them. So now, when I hit OK, you can see here I have a nice quantized ramp. That's pretty cool. But how are we going to use these ramps to give us the Toon shading exactly? So the idea is we know that we can produce a ramp that has any appearance that we want. We can add stops wherever we want. We can set those stops to be whatever color we want. And if we can use one of those ramps, we have the ability to customize the shader without recompiling it each time. But the issue that we need to figure out is, how do you know where to sample the ramp to get your color? And the answer to that comes from the cosine of the angle between the incident light and the surface normal. So that's just, we get that value by just doing the surface normal dot product the incident light angle. And we know, because that's giving you the cosine of that angle, that the value of n dot L is going to be between 1 and -1. Now, of course, if you're going to use this n dot L, you need to make sure that both those vectors are normalized. That is, they each have unit length 1. If you look at cosine function, along the x-axis here we have the angle between the two vectors, and then the y-axis is the cosine of that angle. So I said that the cosine of the angle between n and L would be between -1 and 1. So here and here. So that's the minimum value and the maximum value. Now, I know that if n dot L is 0, it's 90 degrees. And you can see it here because that's where 0 and n dot L would actually be, is right on -90 and +90 degrees. And that is where the light is tangent to the surface point. It's not making any contribution. Similarly, when the angle is bigger than 90 degrees, we're not going to have any contribution of the light to the surface point either. And that's just a part of Lambert's cosine law, which means that if we are looking at this cosine function, whenever the cosine of the angle between n and L is less than or equal to 0, that corresponds to angles between n and L that are greater than 90 degrees. The light makes no contribution. And so it should always give us, in those cases, the darkest colors. However, when the cosine of that angle is positive, that is between 0 and 1, then we should actually be considering the light's contribution and maybe not be the darkest color. So this is the part of the plot that we actually care about. So we can use that dot product as a map to our ramp coordinates. So we can consider the far left edge to be 0 and the far right edge to be 1. And then n dot L, which is the cosine of our two vectors, the angle between the two vectors, would give us our index between those 2 points. So what do we do with any value that is less than 0? Well, if it's less than 0, we want to clamp it. That means we just want to set it to 0 and make it the darkest color. So we can make this simple modification to clamp the values between 0 and 1. So anything that's negative automatically will become 0. And if it's not 0, that means that the angle between the two vectors is less than 90, and then that value, which will be between 0 and 1, will be our index into the ramp. So a couple examples of this math here. So I've got our surface normal here as being pointing up. I was making them pretty simple here. And then my incident light is down. So these are not excuse me. This should not make a contribution. So when I multiply these two together, I end up getting -1, and I clamp that down to 0. And so since I've clamped that down to 0, we end up with the left end point of the ramp, because the light is on the opposite side. Now, if we have our surface normal and our light like this, what is the angle between these two? We know that's 90 degrees. It's perpendicular. We get a dot product of 0, which again gives us the left end point of the ramp. If we have anything like, let's suppose the light is directly overhead, then you would be the dot product of the incident light and the normal light would be 1, and so we would be at the highlight point on the ramp. So that's pretty cool, right? So the question is, how do you create or specify the ramp in your tool? So some tools actually will let you create a parameter for your shader that is a ramp, and you can actually do this in Houdini. And when you see your tutorial materials, there will actually be a video you can watch that does exactly that. It's going to show you how to create a ramp parameter for a Houdini shader. And we'll also have a Unity one as well, and I think it shows you how to create the ramp for that parameter as well. So The only issue is when you actually have one of these ramps as a parameter in a tool, some of these tools have limitations that are placed upon the ramp specifications. So they might fix the number of stops that you're permitted to have to just the 2 endpoints. It might permit maybe 1 or 2 in the middle. And as you saw, in order to do the quantized ramp in Google Docs, I actually had to create a lot of stops that were on top of each other to get the desired effect of the quantization instead of the smooth shading. So that's going to be one limiting thing. Another thing is some tools will restrict what methods are used to interpolate between the different stops. So just be aware that, yes, this works. There's many tutorials out there for how to actually create this kind of shader. But the use of the ramp may be restricted to the tool that you are using. And so the question now I have is there anything we could do that would be simpler, give us the same result, but avoid any potential issues with actually creating this ramp parameter and setting stops? I mean, what if the ramp was specified instead of by the actual physical ramp that you can play with? What if it was just a texture, like just an image? And what I mean by that is what if it just looked like this? And the interesting thing here is that all we would have to do in the shader is point it to the appropriate image. This gives us maximum customizability because we can put as many stops in as we want. We can make it as wild and crazy as we want, as you'll see. And we could have some parts that are smooth shaded and other parts that aren't. This is maximally flexible, and it's very, very easy because it's just an image. The trick here, though, is we need, because this is now a texture, we need some way of indexing our texture. And, well, you knew how to get the position on the ramp by just taking, the surface normal and taking its dot product with the incident light and clamping it so that the values fell between 0 and 1. Well, that's all we need to do to get the U component of a UV texture coordinate. So what about the V coordinate? So the U coordinate is the one going left and right, and the V coordinate is the one going up and down. Well, we don't really need the V coordinate. So you can set V to be any constant value. And you could set it to 0, you could set it to 1, you could set it to 0.5. It doesn't matter. You set it to some value. It shouldn't matter. And now, your texture, since it can be anything, now we can use this texture ramp to create the Toon Shading. So let's do it. So here is how we're going to do something like that in Houdini. And again, you're going to have some tutorials for how to do various similar tasks in the tutorial material. So we start by going to the materials node, and we're going to create a material builder. And the shader is actually really simple. So what these node networks are actually representing is I'm taking that little snippet of code and I've converted it just into this little node network. So you've got your global variables that are a part of the surface that's this material will be applied to. And so I have P, sorry, it's not, P. What I was doing here is I'm computing the angle of the incident light. So I take the point of the light and I'm going to subtract the point and normalize it to get the direction of incident light. So that's the first step that we need to do. Now, in some shaders, in Houdini, for example, the incident light should be a global variable called L, uppercase L. And the other variable I need is the surface normal at the point of intersection, which in Houdini, that's uppercase N. I normalize both these vectors just to validate that they actually have unit length, because that's key for this equation actually working out. The next thing that I do is I take those two normalized vectors and I compute their dot product. Again, this is just a node in Houdini. It's a pre-configured node. You just like right-click on your screen and you can see there's dot product. And in fact, there's all kinds of different math nodes that you can use. Math nodes, vector math nodes, you name it. So I've computed the dot product. The next thing I need to do is clamp the values so they stay in that 0 to 1 range. So I have a clamp node. And now I need to take that value and I need to turn it into a texture coordinate, so a UV. So that's where I'm using this float to vec, which is going to create a vector. And I pipe that into the texture's UV. Now this texture here is where I can specify the actual file name I'm using. And that would be a parameter that you would see actually at a high level. So I take those UVs I just computed as input to the texture. And so this node here is going to do the lookup and give us the color at that point, which we then output the color with no further manipulations. So there you go. Compute the position, texture lookup, there's your color. And so if I take this here as my ramp, and I apply it to the torus, I get this. Now I've got a little rounding error here, but that was just due to a small technical issue on my computer. But you can see here that the dark, so 0 is right here in the dark shade, and anything that's highlighted facing towards the light will be very bright. And so this, I actually have the torus here and the light right here. So the light is shining down on the top of it. And here's another example with a different ramp. Gives us a slightly different result. So this is pretty neat. All I have to do is change the texture to whatever I want, and I get a different Toon Shaded effect. And it's very it's very simple to apply this. Now, technically speaking, we can also, with this technique, give a sense of contours and outlines. And the idea is that you could set the far end of the texture near 0 to be black or whatever color of outline you want. And this technique is very simple, and it sometimes works and it sometimes doesn't. So let me show you an example. So not quite the same purple, but it's the same ramp that I've used. You can see here that this torus, I do have some black outline, but it's not perfect. And in particular, in these areas around the upper rim here, I am not seeing any black outlines. So it can work, but it's not perfect. Here's the dragon doing the same technique. We get some of the details, but not all of the outlines. So it's an imperfect idea. We are going to perfect this idea, by the way, such that you get results that look like these two little figures here. I'm not sure what these are from. I think they're from Mega Man. So this is what we want, and we will be able to get this result, but not from this equation here. We can make a tiny modification to this equation, and it will give us these nice black outlines that we have here, done completely from a texture, which is pretty cool. All right. So far, we've seen that the Toon Shading, you can achieve it very easily by just creating this texture ramp and a shader, which can be created in just a few simple nodes and then applied to your object. The nice thing is it is very, very customizable because you can set whatever you want the texture to be. And the texture can literally be anything. And the shader itself was actually quite easy to implement. The downside of this particular technique is that if the surface itself should have a texture of its own, let's say that your character is wearing a t-shirt, and, well, let's go with this dress here. This dress has this kind of wild orange and fall and winter colors on it, blues and browns and whites. If I wanted to apply Toon Shading to this, well, I can do solid color, but I have no way of extracting the Toon Shading of this pattern. So if something has a label on it, like you've got a remote control, and you want the labels to be present, they wouldn't be present with this technique. So this works for very simple surfaces, but it doesn't work for surfaces that have texture. How could we handle that situation? So as it turns out, there's actually lots of different ways that you can handle it. And I want to show you one way to handle it that's very, very simple. And that is apply the texture to your object as it would normally be. What we're going to change instead is how the lighting is applied. So instead of changing the color of the surface, we're changing the intensity of the light. We're going to quantize its intensity based on the viewing or the incident angle. The idea is that whatever texture you're applying to the object itself, it should already be in the Toon colors. But no baked lighting, just the simple colors you want. And then we're going to use this lighting to give us the quantized shading. So this is the Houdini shader to do that. Again, we are going to need to compute the angle of incident light. So we need to know the vector, the direction of the incident light. And you can do that by subtracting the position of the light from the surface point. Or you can use the parameter L, which should give you that value. And then I compute its dot product with the surface normal at the point of intersection. And we're once again going to clamp it. Now, so I know my position. I create a UV. I'm going to use the texture lookup now, not for the surface color. I'm going to use the texture lookup for the intensity of the light. And then I'm going to multiply the intensity of the light by the color of the object. So that's what I have right here. This is the object color at that point. I have, in this case, instead of using a texture, I've just used a solid color. But it could be a texture, it could be anything. So I'm using quantized light intensity, applying it to our object. And what we end up with is a Toon shaded effect done slightly differently, but now we can have textures on the surface of the dragon. And you can see here it's not smooth shaded. We still have only a few tones. Now this one, there's actually 4 intensities here. We have black, dark gray, medium gray, and white. So you will actually see there are 4 shades of cyan here. So that's a pretty neat thing that you can do. So one of the things that I really want to stress about all of the shaders that I have just shown you and the formulas, we're creating an artistic appearance here. This is not about photorealism anymore. This is not about trying to make a glass look as perfect on your screen as it does on your desk in front of you. We're now trying to create an artistic appearance, which means that we have a lot of freedom to play with the math. I chose to use the clamped value of n.l to give our coordinates for the texture ramp. That's not required. You didn't have to do that formula. In fact, the Unity example uses a slight variation of it. You can do whatever you need to do to create the appearance that you are going for. This is one way to create that universally expected Toon shader. You can be as flexible, you can make it whatever you want. Now, as I said before, using the texture ramp as opposed to just the ramp gives us a lot of flexibility to get some pretty crazy results. So, let's see some crazy results. So in the upper left corner, you can see that's actually the texture ramp I'm using. It's a bunch of black and white stripes. And when I apply it to the model, get this kind of weird appearance. What's really interesting is I'm finding that every shader I apply to this dragon makes it look metallic. At a distance or a quick glance, this shader actually makes it look like it's made out of shiny silver. And if you stop and take a closer look, you realize it's kind of got these psychedelic black and white waves to it. So not silver, but at a distance it does kind of look silvery, which is neat. And here I have a shader or a texture ramp that has a thin black line, a thin white line, a dark turquoise ramp gradient, and a mustard yellow line, and then some more white. And you get this cool effect. So we have some smooth shading mixed in with some harsh quantized colors. And we didn't have to make a new shader to do this. We just changed the texture. That's it. And that's a parameter. It's a very powerful way of doing things. And here's another one where I have a quantized rainbow of, I think I've got 7 colors there. And again, like I said, this dragon looks metallic. It's completely quantized, but it still looks like shiny metal to me. But if you look here, you'll actually see that the dragon itself has been rendered in just these colors here. That's pretty neat. That's a really fun way of doing it. And the possibilities are kind of endless here. So, some things we haven't talked about with respect to this particular Toon shader. Area lights. These Toon shaders were kind of designed to work with point light sources. It's not to say that you couldn't change them to work with area lights, it's just that they're designed to work with point lights. The problem with an area light is that would naturally give you a soft shadow. And it's not to say you don't want soft shadows in your Toon shader. Maybe you do want soft shadows with quantized colors. It's just that most cartoons have very harsh shadows, and so it probably didn't make sense to design these to be worked with area lights. If you want to make this work with an area light, and you still want to do quantization, it's one of those things where you might actually want to consider applying the texture ramp to the intensity of the light. And that would be like averaging all of the ray intensities. Just a thought. Another thing it was not designed to do is caustics or any kind of path tracing, photon mapping, ambient occlusion. Toon shading was not really designed to work within those parameters. It's not to say you cannot create a shader that does that, but this is not something we would traditionally do. Another thing is things like reflections and transmissions. Again, these shaders have not taken those things into consideration. Now, one of the ways that you can actually handle these kinds of effects, is actually doing the toon shading after we've rendered. So render it as toon shaded as you can now, and then clean up the remaining items afterward in a post-processing toon shader. That's one technique. But there's also this thought of how do we make mirrors work in toon shading? Because sometimes we like there to be mirrors, and they'll have like a specific color to them, and sometimes we don't want the mirrors to actually work. So just as an example, so I'm going to have to go back quite a few slides for this. We actually had a real example here. So this is a Bugs Bunny cartoon, the barbershop film. And if you look here, there's this big mirror. There's no reflection in the mirror. The mirror has just been shaded in this case, this kind of gray-white gradient on a diagonal, which is actually a pretty common way of saying this is a shiny piece of metal in a lot of cartoons. But there's no actual reflections. And in fact, if you look at our toon shader that we have right now, you don't get reflections either, but you also don't get that appearance. So those are things that we haven't taken into consideration. Certainly there are research papers that have looked at these particular issues, but a lot of these things are uncommon in typical cartoons. Or you could do them afterward, which is fun. All right. Now, I want to look at the flip side here. So that was looking at toon shading from the render inside the actual 3D scene. Now I want to look at toon shading in the image space, so within pixels. We still have the same goal that we had before, which is we want to reduce the number of colors in the scene to just a few simple tones. So if we have, 16 million colors, I might want there to be only 7 now. So what approaches do we have available to us for doing that? So you could do stuff like color mapping, which is a part of indexed color, which you can do in Photoshop. You could do some kind of explicit quantization. Sorry, this says KNN. It's supposed to say K-means. And the idea here is that for color mapping, you choose the colors. For K-means quantization, the computer chooses the colors. Or, of course, you could paint by hand. Lots of different approaches we can take to toon shading a photograph. So let's look at these methods in a little greater detail and see the effect that they actually have. So first we'll look at color mapping. So to start with color mapping, we are hand specifying the colors we want the image to contain. So we've got a list of n colors, and then for each pixel in our image, what we're going to do is we are going to find which of the colors in our specified list is closest to the color of P. And then that is going to be P's new color. Okay? So that's a very simple way to map the colors in your image to a preset index of colors. Now, the problem with this particular technique is that you have to specify the list of colors, which is also the good side because you also get to specify the list of colors you want to use. Now, how do you compare two colors to say which color is closer? So you might be familiar with something known as the Euclidean distance computation formula. And that's all we're going to do here to compute the distance between two colors. We're going to consider red, green, and blue to be like an X, a Y, and a Z value. And we are going to take the square root of the difference in the red squared plus the difference in the green squared plus the difference in the blue values squared. And that's going to give us the distance between two colors. Now this is not the only way you can compute the distance between two colors. It is one of the most common ways to do it. But certainly there are other approaches. This is the approach we're going to use. So this technique is very easy to implement, and it's customizable because you get to choose the colors. The downside is that if you choose the wrong colors, you're going to get an ugly result. The other thing is that, and this happens because sometimes we think this copper tone is going to get mapped to orange. But when you actually look at the RGB values, it's actually closer to a green for some reason. And it makes it so that the colors don't map quite the way we're expecting. So for example, this is my son's painting here. He's 3. Oh, and of course, green screen, so all the greens are mapped out. But like these oranges and coppers might not actually get mapped to an orange or brown tone, because if you look at their RGB values and you compute the Euclidean distance, they may technically be closer to a surprising color that's different from the one you were expecting. So color mapping doesn't always work the way we want it to. The other problem is that color mapping tends to produce a lot of noise in the image. And that's because when you have an image, there's a lot of artifacting. Your image might be out of focus, there might be some blur, some smooth gradients, there might also be noise due to lossy compression. You end up getting a very noisy, grainy appearance, which is not really something we associate with Toon Shading. With Toon Shading, we expect these crisp, clean lines and solid colors, not noisy. I mean, that could be your desired aesthetic. It's just that's not, when we think of cartoons, that's not typically what people think of. So, for example, yes, I know this photo is blurry. This is a photo I took many years ago. A classic still life scene, just blurry. And when I do indexed color, that's the result I get. I chose 7 colors. And you can see here I got some unexpected results. So I did get some green and red in this bottom apple, but I also got a lot of brown. For example, I thought this red and these lighter tones would end up getting mapped to red or yellow, and it ended up getting mapped to brown. And then in the jug itself, there's some areas around the base of the jug that got mapped to green, which was just bizarre. That lemon looks okay. That lemon's kind of okay. I don't mind that there's green on the lemon. So it's kind of a neat result. But again, some unexpected mappings. And the other issue we have is that it's noisy. And the truth is, this noise would happen even if this wasn't the world's noisiest image. You're going to see this kind of noise on any image you apply these algorithms to. And I will demonstrate that in a moment. So I'd actually like to show you the code, or a snippet of the code, because I think it's important to see how easy this is to do. This is a grayscale Toon Shader that I wrote a few years ago to do a task for me. I was trying to do Toon Shaded stereo 3D images. And what I want to talk about here is, we have 4 hard-coded gray tones. We've got like a darker tone, 2 middle tones, and then white. And we've also hard-coded the thresholds, because again, this was supposed to be a really simple shader. And then I just go through each pixel. I get the color. That's what this line is. Now, a grayscale Toon Shader is different. You might be thinking, well, are you just computing the different distance between the color and the gray tone? And I could do that, and it would give me a reasonable result. But what I decided to do here was, instead of doing that Euclidean distance, I decided to do luminance instead. So the luminance is the apparent brightness of a color, and it's a weighted average of the red, green, and blue components. So in this case, and I know it's going to seem weird that this is actually blue, green, red, but this piece of code was written with a library called Opencv, which instead of doing RGB, it does BGR for some reason by default. I don't know. It's weird. You just get used to it after so long. So we take 11% of the blue plus 59% of the green plus 30% of the red, and we add that all up, and that gives us our apparent brightness. And that is what I am using to compare and figure out which gray tone to use. This code runs really, really fast. It could run a lot faster because there's no reason why this can't be run in multiple threads. But I didn't need it to be that fast, so it's fine. So here are some of the results. So this is actually a ray traced sphere from my own personal ray tracer, not from Houdini. That's why it doesn't have the Houdini logo on it, is because this is a ray tracer I wrote myself. So I have this lovely Blinfong sphere, and this is the Toon Shaded result. Here we go. Now this one actually looks pretty crisp and clean, and that's because this is a nice, crisp, clean, ray-traced image. It's perfect, and there's no compression losses and things like that to it. It's a perfect image. How does this look on a photo? Well, let's take a look. So this is a photo courtesy of the Middlebury dataset, which is a pretty famous stereo 3D image dataset from Middlebury College. This is the Allo image. And I know it looks pretty choppy and noisy in this resolution. It's actually a lot crisper in real life. But when we apply the same algorithm to that, we get this image, and it's really noisy. So that was a beautiful high-resolution image, and we end up with a really, really noisy result. And then that's just because of the gradients in real life and just things being slightly out of focus, natural noise and variation in things, the sensor being imperfect, and so on. The nice thing about my ray tracer is there's no sensor. It's just pure math. So it can have this nice, perfectly smooth result. But real life, you don't get a smooth result. Okay. So that's doing the color mapping, or indexed color, as some might know it. That's me choosing what colors I want my Toon Shader to use. What if I don't want to choose? What if I want the computer to choose the colors for me? I say, give me 7 colors. You choose. How can we ask the computer to choose those colors for us? Because it's tricky. One of the things you might be thinking is, off the top of your head, is we'll just take the 7 most popular colors in the picture. But if your picture is that of somebody's face, the 7 most popular colors are going to be 7 very close skin tone shades. That's not quite what we want for Toon Shading. We actually want there to be some separation between the colors so that we get those harsh quantized appearances. So when we're trying to choose end colors, we actually want them to be sufficiently far apart. And ideally, we want them to all be, equally far apart. So just taking the 7 most popular colors is not going to work. We need another method. Now, there are many, many, many different methods that you can use to use this, but one of the most common, and I actually use this one myself, is called K-means or K-means clustering, and this is actually a machine learning algorithm. It's used for classification. So the idea is just, what does that even mean? The idea is, let's suppose, I'm just going to choose more random stuff on my desk, that you've got a bunch of forks, and because of course my green screen, this turquoisey fork is looking kind of black, but let's say you have a whole bunch of forks and you want the computer to, that there are 2 different kinds of forks. You want the computer to figure out what the two kinds of forks are and separate it into those two groups all by itself. And you can tell people, you can, you know, give some information like this fork has this color and this fork has that color. And let's say they're all different sizes, but you want to do it by color. K-means clustering can figure out and separate the forks into the two different groups. And what's interesting is that we can actually use this to find n colors to use for our quantization algorithm. And how this algorithm works is actually really simple. So, and I mean, yes, there are more sophisticated versions, but the basic version of the algorithm is you choose n random starting colors. And n can be however many you want. Maybe you want 7 colors to start. 7 random colors. Those are our initial groups. And what you're going to do is for every pixel in the image, you assign that pixel to one of those 7 groups, whichever group it's closest to using the Euclidean distance for color differences. After you've done that, and all of the pixels have been assigned to one of those groups, you look at each group and you figure out where the middle of the group actually is. Because your point may be here and all your data might be over here. It just so happens that that's where your random point was. And what you're going to do is you're going to move that starting point to the middle of your group. And then you repeat this process until you make no changes to the means, or the change is some small value. And now you have, once this algorithm completes, you have your 7 computer selected colors. And this is kind of, I've borrowed this image from the Wikipedia page because it was a really good diagram. So you start out, you've got all of these different data points, and the red, the green, and the blue are our initial 3 points. So we're going to divide this into 3 groups. So we create the clusters by taking all of these gray squares and assigning them to the color that they're closest to. So only one goes to this red, this green gets all of these, and this blue gets all of these ones here. The next thing that we do is for each of these groups, we figure out where the middle of the group actually is, and we move our mean to that position. So you can see here, there's the old mean, there's the new mean. There's the old mean, there's the new mean. Old mean, new mean. And then we repeat the process, reassigning each pixel in the image to the group it is closest to until this process stops. And what's interesting here is we're actually creating something called a Voronoi diagram. And we're going to talk a lot more about Voronoi diagrams in our next lecture, because we're going to be using them to do stippling, and it's really cool. And if you're thinking, I don't know how to draw this crazy thing, what's a Voronoi diagram? I don't know how to do all this math. We're going to make a Voronoi diagram by drawing a bunch of cones. It's really cool. Okay, I think it's really cool. Let's make math easy by just drawing cones. So once we've used k-means to identify our k colors or our n colors we want to use, we then can perform the color mapping that we did in the first method to swap the colors for their new values. So the downside is we're not giving the user control over which colors are chosen, but we're giving the computer control. But I would say, generally speaking, the computer usually chooses pretty decent colors. Maybe not what we were expecting, but I'm usually pretty happy with the results. And so this is our lovely old jug again. And I asked the machine to choose for me colors, and so it did. And so we've got some dark browns, some medium browns, and some pinks, some yellows, and some greens. Now, I'm not 100% happy with this result here. I would have liked, there's some green on the bottom of this apple and some green in this apple, and I would have it's clear that it's identified green as being a color, but those pixels didn't get chosen, and I was kind of disappointed by that. Again, sometimes the results for these methods can be a little surprising. All right. So, it's not a bad result. It's not a bad result. It's just a little surprising. I actually kind of like how this apple's shaded right here in the bowl, and the lemon's kind of cool too. So, when we're doing image-based toon shading, the one observation that you should have made, regardless of the method that we have used, whether it was the grayscale, the color mapping, or using k-means, the image results are really, really noisy, which is not something we're expecting for a toon appearance. And again, this is just due to noise in the image, blurs, grain, compression artifacts, because most people are dealing with JPEGs, grain coming from the sensor, wrong ISO values, your hand is shaky, and it ends up with just super, super noisy. What if we wanted to give this a more appropriate toon appearance? Can we do it? Yeah, actually we can. You just got to get rid of the noise. So there's lots of different denoising algorithms that we can use. We talked about 3 different denoisers in our last class. We talked about median filter, box blur, and Gaussian blur. Now I don't want to use Gaussian blur because I do want to preserve the crisp edges of the image. Gaussian blur is great at smoothing everything out. But it kind of does it without consideration of the actual edges in the image. I don't want to do that. For the same reasons, I don't want to do box blur. So I could use a median filter. That's one, because median filter actually does tend to preserve some of the edges. And what's interesting about median filter is that it also tends to perform a bit of color quantization on its own. It does really simplify the colors that are being used because the stronger the median blur is, i.e. the larger the size of your neighborhood, the more colors you're actually getting rid of. There are other approaches that you could take, though, aside from median blur. You could also do something called a bilateral filter, which is well known for also doing edge preservation. And that's something you really want to do is edge preservation here. Because you don't want the colors from one object bleeding into something else that's a very different color. You'll end up with a really weird toon shaded result. So I chose to do a median filter with a radius of 10, which is really high. You do not apply it to the result. You apply the median filter to the original photograph. So this was before the median blur. This is what our toon shaded looked like when we used indexed color. And that's the result we get if we apply the indexed color after the median filter. And immediately we see crisp, clean, noiseless results. Are they perfect? No. The problem with using the median filter in this particular case is it came at a cost of losing some of the finer details in the image. Corners are not as sharp as they were. There's a little bit of weirdness going around the table. We've lost some details. A bilateral filter could improve this, but it doesn't get rid of the noise as good, in my opinion. I didn't do a bilateral filter. And at the same time, we ask ourselves, when we're looking at something that we want to render as toon shaded, cartoons are not take your exact face and paint it cartoon. I mean, that has been done before. And prime example would be a Scanner Darkly. But cartoons generally have exaggeration, a distortion to the appearance of things. So even though this is very distorted, I actually don't think it was negatively distorted. So now let's do the same to our k-means quantization. So this is before and this is after. Still got a little bit of funny business going on up here, but it is a lot crisper and everything else feels so much nicer. I really liked how the bowl and the jug came out. We've lost some details. I can't see the apples anymore. I can't see this lemon back here anymore. But again, this is a matter of you need to play around with the different denoising algorithms before to figure out which one is going to give you the results you want after. Now, this is a technique that you can use in Photoshop. You can do this in the GIMP, whichever of those image rendering tools is your favorite. And if you so choose, you can write the code for this yourself. If you were to ever decide to write this code yourself, there are several libraries I would recommend you use. One of them is Opencv. This is a free open source cross-platform library. It's used everywhere. And it's available for Python and C++ and C. So that's one tool you can use. And in fact, the code that I showed you earlier was actually done with Opencv. Another tool that you can use, which is also cross-platform and free, not as easy to use, but certainly can do it, is a tool called ImageMagick. There's lots of other tools as well. I would like to finish today's lecture off just with a little brief discussion about what are we doing with this toon shading. So it's very clear that we have many different approaches to create that simplified color appearance of objects. So we can take something that had to have realistic shading, and we know how to, either by manipulating the lights or the lighting, the rendering equation, or by actually just simplifying the color with quantization, we can reduce the number of colors and give you that bold, bright appearance of a cartoon. But that's not enough. What I actually want to do here is, instead of looking at those texts at the end, I'm going to go back to the beginning and look at these images again. I should have repeated them. So we know how to produce this color appearance. We know how to produce this colored appearance and this one here. But if I take a realistic model of my face, I don't really have a realistic model of my face, for the record. I used to have one of me standing in a Muay Thai fight stance, but I don't know where the object file for that one went. It was huge. Regardless, if I take a realistic model, super photoreal model, and I apply Toon Shader to it, does it give us the desired cartoony effect? My argument is not necessarily. Certainly it is something that you can do. But one of the things you'll see here with the Wind Waker is that the models themselves are not photorealistic. They're simplified. They're exaggerated. Link's hair is coming off his face like these weird footballs that are magically stiff. His eyes are huge. This is a model that's not realistic. And by applying Toon Shading to the non-realistic model, it created a believable character. So if you want to create something that looks like a cartoon, what I'm saying is it's not enough to take your Toon Shader and slap it on to a photoreal model. It's not going to look right. It might even fall in the uncanny valley a bit. because that's not what our brain is expecting, and we don't really know how to resolve super high resolution horse running, and you can see every fiber of the muscle and every hair with its cartoon shaded. That's very bizarre. So when you're trying to create a scene like this, you also need to create models that are appropriate for the toon shading. So take that into consideration when you use toon shading. It's not just about, hey, I created a cool shader. You need to apply that shader to something that makes sense. Like these simplified models here. And this lion boat, which I won't give you the spoiler for who the lion boat actually is. Or these models here. This is not what a lion actually looks like. It's a very stylized lion, and it makes the stylized shading work. And this is especially true in the Bugs Bunny cartoon, where, again, we're talking about a horse. There's this horse with Broomhilda on it, and the little horse, if this was a real horse, this horse wouldn't be able to walk. But it's a cartoon, and we know that because of the bright colors matched with the exaggerated appearance. So you've got to match things up a little bit. Now, that's not to say you can't create an interesting appearance. So people have certainly created some very interesting results. I like this one here. This is my favorite image from it. So this here was done in post. So this was not done from 3D models. This was actually done from the video feed itself. And so this, you can see here they've applied a certain amount of median filtering to smooth out the colors. There's no noise. You've got the quantization. They've paid very careful detail to making sure that the quantized colors make sense. And then they've also added the black outlines in. So be careful about using something like toon shading, because if you don't get the composition right, it'll still look weird. But that being said, there is great potential to create some very cool scenes using toon shading. But just keep that in mind. Toon shading, creating that cartoon appearance, isn't just about the color. It's about the setup of the scene, the kinds of models you're using, and so on and so forth. All right. So a few review questions here just to think about. The tutorial slides that you will get will have some video tutorials, video guides for how to do various kinds of toon shading in different tools. I see a lot of you are using Houdini and Unity, so I'm probably going to focus on creating guides for those two tools. If you are using Blender, I'll try to find you some guides for that as well. I apologize. I just don't get along with Blender. The more I see of it, the more I wish I knew how to use Blender, but I started rendering in Maya, and then I moved over to Houdini, and I just never caught on to Blender. But certainly I will find some guides for Blender as well. And that will be posted, of course, to Brightspace. In our next lecture, we are going to talk about how to make the lovely outlines and do it properly. And we're going to see there's actually lots of different techniques you can use to make these outlines. We're also going to talk about a few other different things. So for example, I don't have any examples here. We're going to talk about different ways to do the shading. So this is shading with just solid colors. But if you look at some cartoons that appear in things like newspapers, they use things like dithering or hatching, cross-hatching, stippling to depict the shading. And so we're going to take a look at different algorithms to perform those tasks. And I think you're going to find that they're really fun to do. And the lecture after that, we will take a look at how to turn your photographs into Van Gogh paintings. And then the final lecture, because we are approaching the very end of the term, we will look at something called style transfer, which is a really neat machine learning algorithm where you give it an image of a particular style and an image you want to apply it to, and it tries to merge them together. It's really cool. So that is where we are and where we are headed. Don't forget to take a look at assignment 4, and as always, I'm available on Discord if you have any questions or want to share any of your cool results. So we will see you next week.